So this one is Beam on the Edge, Innovation Through Problem Solving. Yeah, this is from my side a little bit more about how Erlang was evolved or developed, or however you want to put it, right? Through it. That's which one am I seeing now? That's that one. That's that one. Me, yeah. So Ericsson, we go here. Ericsson had a computer science lab. Now we're talking the 80s, and we were supposed to look at a number of things, amongst other things, new technology, but also look at how we can solve the problem of making programming telecoms applications much easier. So Ericsson had the AXE switch, which was fantastic. It was very good. It brought them in a lot of money, but it was difficult to develop and maintain for it. One reason, of course, is Ericsson did everything, from the lowest level hardware to the highest level systems around that did that. So we in the lab did a number of experiments. We had our own private switch, a small little tiny switch, which we fixed so we could connect from our Unix machine, which means we could test building these types of applications in anything we could run. I mean, we must have done 30 or 40 different ones, some very small, very trivial, some quite large and quite complete. But the problem here, why we went on with Erlang, of course, was we didn't think any of the solutions we could get hold of, which existed in those days, were very good. And then we started working out what is the problem, really, what we're trying to solve. So these features here, these 6 points come from a thesis by Bjarne Dekker, who was the boss of the lab at that time. He had some other things that other points as well too, but these ones I felt most important for this. Describing the problem domain, right? So it has things like a very large concurrency because you're doing a lot of things. You might have hundreds of thousands of connections, tens of thousands of calls going on, etc., and the switch doing stuff. You have timing constraints. Things have to happen within a certain time or at a certain time. This meant, for example, the system must never block. That's just not allowed. You need distribution. If you want to make a truly fault-tolerant system, you need at least 2 computers. Nothing strange here. We had the continuous operation and the software maintenance. That was the problem, that the system must never go down, or never be taken down either, for that matter. So if you're going to do software upgrades and things like this, you have to be able to do that while the system is running. And then, of course, there was fault tolerance. So things are going to go wrong. It's not an if, it's a when. But the system must be able to handle those errors. And the interesting thing about this, of course, is that there's nothing about telecoms in this. That's something we didn't realize, at least I didn't realize until later, but that's the problem. However, if you look at these points, you see something. They both say a lot, but they also say nothing, right? So what does this mean from our point of view for building this type of application? What does it actually mean? Right? And this is something we had to work out ourselves in one way, that what does this mean for this type of system, and how would we develop a system that satisfies these requirements? So there were many thoughts going on at the same time. I mean, it started off with Joe. He wrote down some rules, which he thought for telecoms, and someone looked at those rules and said, oh, that looks like Prolog. And Joe, who didn't know Prolog, said, yeah, looked and said, it does, doesn't it? So then he started working on an interpreter for these rules, talking with our small switch. Then you get into the problem, how do you do all these things, right? So, yeah, we could run one call, but if we want to run multiple calls, then we have to start thinking about concurrency. And if you want to do fault tolerance, then you have to start thinking about, well, what happens when these things die, et cetera, et cetera. And this forced us to think a lot about what was the actual problem from the point of view of providing a solution from it. So saying you have to have lots of concurrency and timing constraints, what does that mean for building a system for solving this type of problem? And that means, how do we build, how can we create a language and an architecture that does this for us, or can be used to do this? So I mean, the top level goals, the problem domain was very nice, but it doesn't say what we're doing, how we're supposed to do things, and et cetera like this. So the problem was that we had to work out a language and an architecture at the same time. So if we put features in the language, can we use these in the architecture to build the type of systems we want? And that gives us both thinking of how the language should be, what the architecture should be, how the problem domain relates to these type of architectures, things like this. So we're working at all these levels at the same time, right? That's what the diagram here with the thinking, the ideas, and the experiments. So we had some ideas. We would try to implement those ideas. Then we'd come back and see, do they work? Can these ideas then be worked on to increase the system, or do we have to go around and rethink how we want, what features we want in the language and the architecture of the system? And these worked very well. These work together, right? So we're thinking about language features. At the same time, we're thinking about how would you use language features to try and solve this problem, and at the same time thinking, what is the problem from our point of view? So everything worked together for it. And that's why some things are so extremely simple to do in Erlang, because that's what it's designed to do. I mean, you can write a supervisor in one page of code, literally. Why? Because that's one of the things Erlang was designed to do, right? And you can add things in your servers and interface between clients and servers to detect when clients go down. It's only a few lines of code. Why? Because that's what the system was designed to do. So all these things work together, right? And this sort of, we evolved our view of the world, how it should be done. Joe and I knew very little about telecoms when we came. We could make a telephone call, that's about it. Mike Williams, he'd worked at Ericsson for a number of years before developing systems, so he had a much better feel for the actual problem. We had other people in the lab who came up with ideas and things like this. We were quite happy to steal things from everywhere else. We weren't really, didn't really have any restrictions or what ideas we'd use. But that was our view of the world, and our view of the problem and how you would solve it, and the features this solution would have. Right? But we also were lucky that we could work together with another group inside Ericsson in a project called the ACS Dunder. They were looking, if I remember correctly, at making an architecture for smaller exchanges. So they were very much from the problem side, or from the product side there, working for this. And we had a collaboration with them. I cannot remember how we actually got into it. And they worked, so we tried to explain our ideas of how you would build a system using Erlang and our thoughts for the architecture. And they would try and come back and try and explain to us what the actual problem was, what the real problem was, the real world. And this went round and round and round for a while. And it took us a while for us to explain our ideas, for them to come back, and eventually they built a prototype, the first prototype they had for this, using Erlang and our ideas for building systems. And this was very nice because they made something around 15,000 lines of code. So it was their prototype, so they had things in which for them were important. This was not our way of doing things, this was their problem solving. And they found that using our architectures and the language, of these 10,000 to 15,000 lines of code, if somewhere between 600 and 900 lines of code were correct, they could handle errors everywhere else, and the system would recover from them and keep going from them, which was what we were trying to do. But they were very good because they came back with a real-world feedback for it. Were our ideas good? Were they useful? How would we have to modify things to make them really useful from their point of view? Which we did. That's the second loop here. At the same time we were in this loop, the internal development, we were still going on in our own internal loop, but thinking about things, how we would prefer to solve them, and then come back and then talk to them about it and so on. So we're having multiple loops going on the whole time. So, and that's how our view of what the problem was, or the low-level problem, how to solve it, worked. Right? We just kept on going. So where do we end up? I think people have seen this before, but from our first principles here for the solution, you need lightweight concurrency. We wanted lots of things going on at the same time. You want a large number of we end up in we call processes. If you listen to Carl Hewitt, he was talking about actors, and they're pretty close, very close to it. So we came to basically to the same place. He came from the theoretical side, we came from the practical side. for this, we found this is where we arrived, and this was something we could use to solve our problem. So it's your lightweight concurrency, lots of processes, lots of context switching, things like this for them. We need asynchronous communication. Synchronous at a low level is bad because it blocks, right? And we could not block. We need process isolation. From our view of handling the system, when something went wrong, processes would start dying. That was how we would handle errors for it, the let it crash principle. That means that they have to be able to die without affecting things for other processes. At the same way we had the basic concurrency principles at a low level, we'd also have the error handling principles at the low level. These were so fundamental to the problem. It's not something you put on top in a library. You bake it in at the low level. Continuous evolution, that meant how we handle code and can reload code while the system is running in a well-defined way, so you can build up a system managing that. And the soft real-timeness, the non-blocking. So there's a lot of support in the language and in the implementation of the language and in the architecture on top for doing things in a non-blocking way. And if you look at how the beam has evolved over the last 25 years, there's an awful lot of effort going in to make sure it doesn't block. It is very hard today to block the beam because that's a fundamental requirement we have. We had a few other ones. We wanted a high-level language. This is the 80s, right? C and Ada were high level in those days, so we wanted a high-level language. We wanted the language in the system to be simple. Simple to understand and hopefully simple to learn and to work with as well too. But you want the right level of simple ideas. You want a few simple ideas. If you get them right, then you can build everything you want on top of that. You don't want the complexity at the low level. The complexity is in the solution, not in the thing. And we also found providing tools for building the system, not solutions. And this we found out the hard way, because we sometimes tried to think, and you have to be careful when you start thinking. And we're looking at the, well, you do. We were looking at the problem. We tried to guess how the problem should work. Could we help them by putting features in and help them solve their problem, right? And we usually got it wrong. So what we came up with was it was a nice solution, but it wasn't the problem, right? The classic one's the pipes. I'll just take a minute on. So the idea was if you have an A calling B and you want to redirect the call from A to C. So we thought, wouldn't it be fantastic if A didn't have to know who they were talking to? They'd just send down to the other side and then they could move the other side and they wouldn't have to worry about that. So we came up with what we call pipes. So you send things down a pipe and you receive from a pipe instead of from message queues. You had a pipe algebra so you could merge pipes and munge them and combine them and everything like this for it. And so it was really fantastic and it worked. So we gave these to the ACS Dunder people and said, can you use this? And they came back after a while and said, yeah, we can use it, but we don't need it. Because our basic idea of being able to redirect A's communication from B to C in a transparent way was wrong, because they cannot do that. Before you could do that, A has to know who they're talking with anyway, so the whole basic premise was wrong, right? So we just junked pipes and went back to sending messages. When pipes were in, at that time, that was the most large and complex part of the whole system, getting that right. So yeah, so we were working on understanding the problem at the same time we were providing solutions for it. Where we ended up, well, as you know, this is the language. It's a simple functional language. Nothing strange about it. It's got typical functional language features in it. It's dynamically typed, however, right? And there are no user-defined data types. Both Erlang and Elixir try to fake it. Erlang fakes it using records, which are tuples, and Elixir fakes it with structs, which are maps. But there are no user-defined data types. This gets back to the code loading. The concurrency model we found, we want lightweight isolated processes. That's the base. We need asynchronous message passing. That's it, right? You send a message, basically send and pray. You send a message to other process. It might get there. You don't sit and wait for anything in the message passing itself. It's a very basic mechanism. And on top of that, you can build whatever level of synchronous communication you want. I'm not going to show you an example, but if anyone's interested after, I can show you a very simple example from inside the gen servers. It's a selective receive mechanism. I choose which messages I want to see now, and I'll leave all the rest till later, which means you don't get a combinatorial explosion of being able to handle every message everywhere. And there is no global data. We don't do shared, we don't do mutable, and we don't do global. The error handling side, we have the concept of links. We link two processes together, and when processes die, they send exit signals to the process they're linked to, which will kill those processes, and they will go down. Then you need to trap exit so you can use the linking for monitoring as well too. And I just want to end up with a very small little example here. This is a bit of toy code. We could run this on our machine in the lab, and we could actually talk to our switch and control our switch. So if you see the TeleOS library here, that was actually communicating with our little switch and doing things. So this was setting up a call. And here, what you see here is we're in the ringing state. So that we've dialed a number, and the phone's ringing. We hear the ringing in our phone, and the ringing's on their side. So we've got the A side and the B side. And again, splitting up into separate processes, having multiple processes doing something in one call, even a simple call like that, made things much simpler. That's why we have multiple processes. You might have 4, 5, 6 processes per call while the call is going, handling different parts of it all connected together. And when you look at the A side, for example, well, that side as well too, the A side, if it gets an on hook, that means the person we're talking to, well, if we look at the A side, this is the person making the call. So if we get an on hook, that means the person making the call has put down the receiver and not waited. So then we send a cleared message to the B side, saying now it's cleared. Then we stop the dial tone and we go back to the idle state by calling the idle state function. So on the B side, if we get it cleared, that means that the A side's hung up. So now we stop the ringing and we go to idle state. However, if we get an off hook on the B side, that means the person's answered. We stop the ring tone and we tell the A state that we're answered, and then we go to the speech state by calling the speech state function. Now the A side then gets an answered, and it stops the tone and it tells the switch to connect. So the connection is set up by the A side here, and then we go to speech. But both of these cases, both sides here can get a request from someone else talking to me. I want to connect to me. That's what the C's is. And both sides have to immediately reply, reject it, because they're busy, right? And then they just keep on ringing, and everything else we ignore. The thing here is these C's have to be handled immediately. So if we were sitting in synchronous communication, then we couldn't do that, or it would start becoming extremely complex. So this is just an example of using the asynchronous communication at the low level. It means we can handle a lot of these things very simply, right? Just a very simple case for the code. And this got into it, right? This is where we ended up. But it was a long evolution of us both trying to understand the basic idea, the high-level concepts in there, how these would relate to the low level of building the actual switch or things, the system for it, and how we could make a language and an architecture at the same time which suits doing that type of thing. So all these things were going on at the same time. We had the whole thing was evolving as our ideas evolved, as our understanding or the feedback came back, evolved, so the whole thing was working at the same time. So this took a number of years to do, the whole thing for it. And in that sense, we were very lucky because we could have these years for it. We didn't sort of have a 3-month break and then deliver what we had, right? And that's the basic idea for it. Yeah, that's my part. Now, getting on to Frank. Now we're getting interesting, right? So, well, one thing I can just, quick things. One thing I can say here is that I've always been very impressed with what people do with Erlang, to be honest, right? I mean, the first time someone came and said they'd done a web server in Erlang, I thought, why would anyone want to write a web server in Erlang? Well, you find out afterwards, yes, it is a very good suggestion for. And I'm truly impressed with what people use the language for. In this sense, I'm saying exactly, from my point of view, Erlang and Elixir are the same thing here, so there's no big difference here. And what Frank's done with it, and the nerves, I think is really, really impressive. So yes, have a go. It's all yours, mate.
All right, so thanks for that introduction. This is a very humbling moment for me right now. But I wanted to talk a little bit about nerves and about the evolution of nerves, some of the things that have happened over the past years. Some of you may remember me from 2014. I don't know if you recognize any of the people in that picture, so I'll give you a little context of what's being shown there. What that is in 2014, this was one of my first nerves presentations. I built a little IP camera, showed it out to everyone looking at me. So you can see I think there were about, I don't know, 6 people in there. So that was 2014, Erlang Factory. That's where it began, and it's kind of, when I think back about the history of this, these things take a while. There's a lot of iterations going on. So anyway, let me get into the domain. This is not where I thought I was at the beginning of nerves, but this is the term that a lot of people are referring to for where those of us working on nerves operate. And it's called the Industrial Internet of Things. Probably a lot of you have heard of Internet of Things, embedded systems. Now the word that people are using a lot is industrial, and that more is the application of this to industrial processes that use these embedded systems. And nerves, I think, has found a little bit of a home in this domain. So I want to show a couple examples to give you all an idea. So here is one of them. This is, I always get this wrong, whether it's a tugboat or a towboat. The Erlang VM is in both of these. So the problem being solved in this picture is that these boats, these commercial boats, have a lot of sensors and actuators, and they all need to be fed to a central place to be aggregated and presented to the captain of the boat. There is an Erlang embedded system inside boats like these, a whole lot of them on the Mississippi River Valley, that does this job. Some of the features of it, it receives a lot of data from a lot of sensors on this, and as you might imagine, it has to be robust, fault tolerant, a lot of the terms that we use all the time here. Okay, so moving on to another example. This one's a warehouse. So the problem that this company is dealing with, they have a rental clothing business. So the idea is that you sign up with their service. This is Latote, and they will send you clothes through the mail, or you can get them through a store, I think now. And then you wear them, send them back. They process the clothes, then carry them on. Well, behind the scenes, they have a whole bunch of warehouses. There's a lot of automation, and it's kind of hard to see because the actual computers are really small on this scale. But the idea is you can see all the clothes being lined up. There's washers, kiosks for workers. There's packaging stuff going on. All that stuff is using little embedded systems to kind of coordinate and automate parts of it. That runs the Erlang virtual machine. Here's another example that you might not see too much. So this is a UPS. I think most of us know what UPSs are. It's basically a battery kicks in when your power goes out. Well, it turns out data centers have the same things, which probably makes sense, but they're a lot more complicated than the ones that you buy in your home. This particular one, this was made by Schneider Electric. It runs Erlang on the inside. And I think one of the things that I learned from this was they went to the Erlang VM for the soft real-time capability, and also due to the libraries that are available in our ecosystem. So kudos to a lot of us, or a lot of the people around here who have worked on MQTT, Modbus, SNMP libraries. That was a big deal for that group. So the last setup that I wanted to show, so what you're seeing, what the problem trying to be solved in this picture is, say you live in a big city, in this case, New York City, and you want to have fresh vegetables in winter or whenever. So the idea was let's get these big warehouses in Jersey and just rack up all these pallets of plants and grow them indoors. So they're organic and pesticide-free because they're indoors. So on each of those pallets is a little computer that runs the Erlang virtual machine that keeps the plants happy with water, light, tracks a bunch of other attributes of them. And they run their service or their system, or they automate it with back-end systems. They're also running Erlang and Elixir. So, all right, so hopefully that gives you kind of a feel for this domain. The crux of all this is that the types of programs that we're writing run on embedded systems, and inside each of those little pictures, there's a little board. Maybe it's like this one, maybe it's a little bit different, but all the code is self-contained in that board. It's a single-purpose thing. It's not like a server or your PC that could run just about anything, but it has a purpose in life, and it's to either make the boat go or keep the plants happy or any of the other ones. So let's rewind back to where I was before I started Nerves, and this is kind of a familiar situation. I think of a lot of people I've talked to here who have been in embedded systems before. We all kind of were going through this process where we had these huge code bases that were starting to grow. They were all C, C++, still a whole lot of them are C and C++. But we start getting these new requirements. We had to network them because, right, we wanted to move our brains to the cloud because that provided some very obvious benefits on a business level. Then the other thing that happened is we had to move our code. We had to use other people's code, right? So there was this happy time in my career. Well, okay, there are trade-offs, but all the code was built in-house. Then all of a sudden we had to start pulling in all this open source software and libraries, and then our systems now had to rely on their reliability as well. That was a pretty big deal. So let's slice this from a different angle. And what are the attributes of a lot of these embedded systems? So message-based. So embedded, I think we all knew that share and state was bad. Maybe we didn't do it, but it was certainly communicated very widely in the community that this is the route to go. How do we recover from failures? Well, at one level, we all had watchdogs in our systems that reboot the system when things went terribly bad. But we also had little kind of supervisors, mini supervisors on our processes that when they crash, we just start them back up. So I hope people are kind of getting a feeling that we might be going somewhere with this. And then the other thing that happened to us was that, or in my experience, was that the processor prices started really getting cheaper. So we were paying thousands of dollars for some of these early processors, and all of a sudden you could put Linux and Erlang, and even though on these processors, and these things started getting within the range that we could use. So just to give you an example of how crazy this has come. So this is, you can't see this, it's really small. But this, I think someone was able to get these for like a couple dollars, and this one runs Nerves, Erlang VM, and Elixir on it. So there's a trade-off. So before everyone gets excited and like, okay, you can go really cheap. You are trading a few things off with going that inexpensive, but it really comes to show how far we've come with getting these high-powered processors in these little packages that can be embedded in these devices. All right, so let me talk about Nerves now. So for those of you who haven't looked at the website or seen or heard about Nerves, this is just a set of libraries and tools to build the embedded systems that go in these devices that I'd shown before. So Elixir is highlighted on this, but there's an awful lot of Erlang, and like you would imagine, our tooling is Elixir native, but if you can get past that, you can certainly develop to your heart's content in any of the Beam languages. All right, so what's the core? So the core is Erlang. The one thing that we made a decision early on, so there's actually a lot of thought around this, but we finally settled on using the Linux kernel. Why did we use the Linux kernel underneath us? It was for device drivers. So when you're building these systems, you have to get drivers from somewhere if you don't want to build them yourselves. So there are a bunch of options. The kinds of systems that I was involved with, the drivers were only available on Linux, so went to Linux. Now, how do you connect the Linux kernel with Erlang? You need to have an init system. We don't use a standard init system. There's no systemd in Nerves. I guess in theory you could do this, but what we do, the default route is we have a little program called erlinit. The Linux kernel starts it. It sets up userland in a happy way that can start the Erlang VM and start your release. So the other part of this is kind of an acknowledgement that the whole world can't be translated to Erlang. We wish it could, but that's just sadly not happening for a lot of our applications. So we use a package called buildroot. So buildroot has all these recipes and all this knowledge for compiling down big things. Like say I want to have, say I'm making a kiosk and I need a web browser like Chromium or something like that. That is a really complicated package to build. Buildroot knows how to build it, which is killer. If you need to have something like that. But I mean, there are simple examples like OpenCV and all these other packages. So now we get to the fun part, the Erlang Elixir ecosystem. You can pick out libraries, and there's certainly now a lot more. Plop those in your program as dependencies, make a release, an OTP release. So this was, I just want to say a couple words about OTP releases. This was one of the things that sold Erlang on me, because my experience building embedded devices, I want to minimize the moving parts, right? I have to maintain the whole system. Having few moving parts to maintain and understand is so nice. So the whole OTP release idea with pruning out just what you need, having a fixed init script that didn't change, it was very deterministic, that was pretty cool for me. And aside from the language features, this got me interested early on. All right, so that happens. We have our OTP release. The tooling will create a binary which is frequently copied to micro SD cards for people getting used to this, but it doesn't have to be. There are other options there. And that's plugged into your embedded system or programmed in however you do. So just one little caveat on this, because it's kind of one of the things that makes nerves, which is the packaging and how you do updates. On that SD card, this is like a high-level block view of what you'd see. So those of you who've seen this before probably recognize the master boot record. It's kind of like a table of contents. But the part I want to concentrate on is that root file system. So the output of nerves is a compressed, immutable file system. So it's small, just what you need. We plug it into either the A slot or the B slot and swap. So the first boot, you'd go for A, for example. Firmware update comes in, write it to B. Everything's good, everything checks out, signatures, everything's good. We'll reboot into it. If there's a problem, you can set it up to revert back to the old one. So that's how you can keep your systems up a little bit longer on boo-boos on making firmware releases. So anyway, that's how it works. I think it's familiar to a lot of people in this domain as blue-green deployments. And then the other thing that we did recently was we introduced this open source Nerves Hub server. So the idea is that you have all these devices in the field. The easiest way to update them is not to take a micro SD card and plug in them or to SSH over to them. It's that they call home, and there's a server that maintains what software should you be running. Is it the right time to update? And then update. And there is a lot of depth on that. That is actually one thing that has gone through many iterations before it got to the open source world. All right, so now I want to take a step back, right? I want to, we're talking about innovation, what's happening. Nerves didn't happen all at once. We're still iterating and improving in a lot of areas. But I wanted to highlight a couple areas based on some of the pictures that you've seen. And this first one, the boat, the Rose Point Navigation Project. I think many of you I don't know if this is well known, but I actually quit working on nerves for a couple of years. So 2014, you saw that, I presented there. It didn't get much traction in the beginning, and I really wanted to use it in my systems, but C and C++ was the way to go for everyone I talked to. So I kind of got a little bit depressed about this and moved elsewhere. And then all of a sudden, out of the blue, Garth Hitchens contacted me and said he was having trouble building the system that goes in this boat. It was running out of memory, kind of slow, and he was very interested in porting things to the Erlang VM. So he did, and he actually wrote it in Elixir. Called me up for some help in getting this started, and his system worked really well, and he was able to ship it. That I'm never going to not appreciate what he did for this particular project in getting a lot of us back into this area. So anyway, thanks to Garth on that. The specific things, the technical things that he had an impact on were firmware updates, right? The firmware update situation got a lot more sophisticated, and Mac support. So those of you who knew me back in 2014 or maybe saw this, I was a hardcore Linux person. Turns out the Elixir community is widely Mac-based. And so what I didn't know was everyone was starting up VMs on AWS and other services to do their compiles, which was kind of painful, if you can imagine the development cycle of building remote then downloading local. So he had a huge impact on making this system easier to use. And Justin Schneck, who I work with a ton, put that into a lot of code to make Nerves what it is today. All right, so LeTote, what happened there? So as many of you know, Justin Schneck, I work with a ton. LeTote took the faith in Nerves and him to actually fund him to do a lot of work on the Nerves ecosystem. So I did not have that. The Nerves had been a hobby at this time for me. So those of you watching the Nerves development over the past few years, that is specifically attributable to LeTote building out their internal infrastructure and allowing Justin to open source and having the freedom to build things that may not have been necessary for them, but were certainly great for our community. Oh, and the other thing, all of you working on kiosks, that was a bit of work. So that we iterated a lot. Just to give you an idea, the firmware sizes that I normally make with Nerves and Linux are like the low tens of megs, and the kiosk-based ones usually are in the 100. So they're big images, big complex images. So that was made us refine a lot of aspects of the whole Nerves ecosystem that supports that kind of scale of software. All right, moving on to this next one. This one was interesting. Schneider Electric is very traditional in their software development. They had Windows systems. So those of you on Windows, which may be 0 in this room, but if you are there, getting the user experience a little bit better on that system is partly due to them. The other thing that's due to them is for stressing out the networking stack to no end. They added more features to the networking stack than I thought imaginable. So as any of you who attended my talk yesterday on VintageNet, well, they were the ones that pretty much broke the previous network stacks that we were using on Nerves and made us rethink how that would be structured. So thanks to them on that. And then the final one, so Bowery. And the other thing I have to add on the farming. So farming seems to be like a interesting topic for people using Nerves. There's more than one farming company here. Many of you may be aware of FarmBot. So that's like you put the FarmBot in your backyard and it's a little robotic farmer. And then there's Bowery, which is massively large scale. And there are a few others that are doing this. I think these kinds of applications with the farming have been incredible in spreading the message that Nerves is a viable system for building real products. And I just want to say that in my domain, there are an awful lot of failures. So I just highlighted a few, right? There were a lot of things that I didn't talk about that, people tried to use Nerves and projects that failed for maybe not, a lot of times not even technical reasons, but it just takes a while to get these kinds of projects out there. Right? We're building stuff. It's not like posting up a web page. There's like a lot of money that people have to pour into these things at every stage to deliver. And you can kind of imagine, like this one, there are thousands of platters there. So then each one has a computer in it, and that computer is probably the least expensive part of the whole thing, if you can imagine. So anyway, this is my story for now, and we'll definitely be continuing. This is all super fun for me. I cannot tell you what a pleasure it is working with everyone, and especially to be able to share the stage with Robert. This has been awesome. So thank you everyone for inviting me. And I just want to part with, so let's all keep on innovating, and I'm looking forward to working with everyone here. So please keep in contact with me. I'll be around. So thanks.